Hi and welcome everyone to this installment of the International Field Emission Society's lecture series on atom probe tomography. My name is Peter Felfer. I'm a professor at the University, the Friedrich Alexander University Erlangen-Nuremberg in Germany. And the topic I will be talking about today is Introduction to Ultra-High Vacuum Systems. So what I will cover in my lecture, or lecture series really, so I've decided to make it small palatable bits of information so they don't have to sit through one entire, 2-3 hour lecture, but rather, chopped it up a bit. And what we'll cover in that series is essentially how to deal with ultra-high vacuum systems, what the fundamentals are, what the limitations are, and what the design principles are, so that you are actually able to understand how we can create the conditions in an atom probe system that we need to conduct the experiments. And I will hold my lecture today by using a PowerPoint presentation. So you can see I will show you slides on a PowerPoint presentation. I will also use a drawing tablet. And that's actually the main thing I will be using. So I will develop most of the lecture content on the drawing tablet, and you will be able to get my drawings that I've made as printouts for you to work with later. And I also have set up a camera where I can show you parts and show you some demonstrations about handling of ultra high vacuum systems. And you can already see, there's aluminium foil underneath all of the parts, and why that is, I hope you will have understood by the end of the lecture, because if there's one thing about ultra-high vacuum systems that you always need to remember is that we need to keep everything very clean. So we use a lot of aluminium foil because when you take it out of the packaging, it's very, very clean, and you can just put it somewhere and also keep your atom probe parts clean. And with that, I would like to first give you a little bit of a rundown of what the conditions are that we need to run an atom probe experiment, and then show you what typical systems look like, and then we will go through the lecture content of what I will tell you in this lecture. And as I've mentioned already, I'm working here at the Friedrich Alexander University Erlangen-Nuremberg. And in my group, what we do is we do a lot of atom probe tomography. We also do other things, but the thing that we do most is atom probe tomography and field ion microscopy. And for that purpose, we run commercial equipment from Kamika, and we also run home-built instruments that we partially have gotten the design from other groups, for example, from the group in Stuttgart, and partially that I've designed myself, and we've built ourselves here in Erlangen. And that was the wrong button. Sorry. And so the first thing I want to show you is what for a typical atom probe and film system layout, what are the cornerstones? So the cornerstone is obviously we need a very, very high vacuum level. And I'm just seeing right now that there is a typo here. Of course, the vacuum level in the measurement chamber should be less than 10 to the minus 9 millibar, not 10 to the 9 millibar. That would be a lot of pressure, obviously. We want less than 10 to the minus 9 millibar. The amount of background that you get in your measurement might depend on the pressure that you have in the measurement chamber. So typically we aim for lower pressures in the range of 10 to the minus 10 or maybe even 10 to the minus 11 millibar. Then we need a temperature that's low enough to impede surface diffusion. So you've probably heard a lot about that already in the previous lectures. And that means we need to provide very low temperatures, typically less than 80 Kelvin. So 80 Kelvin would typically something you can reach with liquid nitrogen cooling, but we need to be below that. So we need to have systems that cool with coolants other than liquid nitrogen. Historically, people used to use liquid hydrogen, which is a very, very good coolant with a temperature of about 20 Kelvin. But for safety reasons, this is not actually a preferred coolant these days. These days we use either closed cycle cryostats or we use liquid helium, and we'll go through that. And in both cases, we'll go through how to generate the vacuum, how to maintain it, and how to measure it. And same for the temperature. We're looking into how to generate the low temperature and how to measure it. Then we need various signals to go in and out of our vacuum system. Obviously, we need to provide high voltage. We need to provide voltage pulsing. So we need to provide high voltage and high frequency. And for the voltage pulsing, we need to provide high voltage and high frequency together. And to read out a detector, we also need a read out a detector, temperature measurements, stage movements, and so on and so forth. We need various signals to go in and out of our ultra-high vacuum system as well. Then we need viewports. We need viewports so that we can see how we manipulate our sample. And also possibly to couple in a laser. On top of that, we need to have some method, some way to get the sample in and out of the system. So we need to have valves, we need to have transfer rods and the like. And this is also something that's very important for us so that we don't need to build an atom probe system every single time you want to measure a new sample. You might laugh in 2020, but in the very early days of field ion microscopy and atom probe tomography, it was actually often the case that you had glass instruments, and those instruments were one sample, one instrument. Also, in many cases, we want to have the ability to store some samples inside. That's just if you have a lab where a lot of people are using an instrument, you want to have a sort of constant flow of samples in and out so that you don't lose too much measurement time, and you might want to have some sample storage, a buffer chamber. For the sample exchange, we've got a load lock, and you might want to have a buffer chamber. That's not really required, but I would say most instruments have that. But some instruments, especially for fundamental research, where sample throughput is not that much of an issue, might not have a buffer chamber. So what does something like that look like? So here I've got 3 different systems for you, just to show you what the whole system generally looks like. And you can see, so the left 2 are atom probes, and the right one is a field ion microscope, which could also be used as an atom probe if you put an atom probe detector in. And the general layout you can see is a lot of stainless steel. So we've got a lot of stainless steel that's being used here, just simply because if we want to have that high vacuum that we need, that ultra high vacuum that we need for our atom probe measurement, we will need to heat up our system to an elevated temperature above typically 100 degrees C, usually much higher than 150, 160 degrees C. To get rid, while we're actually maintaining pumping, so that we can get rid of surface contaminants that are inevitable when you open the system. And this is also why we have a load lock and possibly a buffer chamber, because a load lock allows us to interface to air. Air has moisture in it, and the moisture is going to absorb on the walls of your chamber. Yeah? So we can pump down the system, the load lock to a low pressure, and then go from the load lock into either the measurement chamber or buffer chamber. So here on the left side, you've got a system that we've built here, and you can see here we've got a load lock, here we've got a buffer chamber, and here we've got a measurement chamber, and here we've got a big cryostat to provide the cooling. Here we've got a commercial system from Kamika, a LEAP 4000. It's a very popular system, and you have the same layout. So you have a load lock here, you have a buffer chamber here, and you have a measurement chamber here. And you can already see there's a lot of, in a measurement chamber here on this atom probe, it's on the back side, you can really see it, but on this atom probe here, you can already see you've got a lot of signals going in and out. And here we've got a little bit of a simpler system. So in this system, we've got a load lock and a measurement chamber. Here we've got the field ion microscopy screen, and we have to have one magnetically coupled transfer rod to transfer all of the samples. Whereas here in the Kamika system we have 2, and in our system on the OxCAD we have 3. Yeah? So it's usually just a matter of price and space, and how fancy you want to go with your vacuum system. But fundamentally a vacuum system like this one here is actually enough. And I just want to show you what a typical ultra high vacuum system looks like if you do if you essentially make a system drawing And what we would have is we would have some kind of measurement chamber, okay, that is connected via, make this a little bit nicer, that it is connected via some kind of valve to a buffer chamber, which again is optional. And then you might have another valve going into a load lock. And we have to have some transfer rods that allow us, we usually draw them a little bit like this, to allow you to go from chamber to chamber. So the transfer rod would manipulate your specimens. Then somewhere in the measurement chamber you would have your detector. We would have your detector. And here you would have your sample on some kind of mount. And on top here you would have some kind of cryostat, which very often these days is a so-called Gifford-McMahon cryostat or a Stirling cryostat. We will get into that. Or it could be liquid helium cooling, liquid hydrogen cooling, and the like. And you need to connect that via some means to your specimen. And then on your specimen, you've got a temperature measurement, and the temperature measurement obviously needs to go outside as well. And here usually you have some manipulation options as well. And this system is then connected to a pump. So this is the symbol for a pump. And we can have various types of pumps that we will go through. But essentially this is very often is a so-called ion getter pump. Or it could be a non-evaporative getter pump, or it could be a turbo pump. But what all of these pumps have in common, all of these ultra-high vacuum pumps have in common is that they cannot get you to ultra-high vacuum by themselves. So you need to have a backing pump. Okay, so we need to have a backing pump. And the backing pump can also be various types. And backing pumps could, for example, be a rotary vane pump. And don't worry, you don't need to know yet what these pumps are. We will go through each one. Rotary vane pump or a scroll pump. Or it could be a roots pump, or a membrane pump. Each of these pumps has upsides and downsides, and we'll go through each one of them. And the same thing here. Same thing here. You need to have some kind of primary pump and some kind of backing pump, and on the load lock itself you can sometimes get away with just one mechanical pump. So we've got a coating system where we, for example, only have a mechanical backing, what you would usually call a backing pump, pumping the load lock, and that's sufficient to work in the high 10 to the minus 9s, which would be good enough to move things into a buffer chamber. But typically we have a backing pump here as well. So we have a primary pump here, and we have a backing pump here. And we have a backing pump here. And let me just make a little divide here so that you get an idea that these are the primary pumps and these are the backing pumps. Obviously, for price reasons, very often what we do, and efficiency reasons, very often what we do is to maybe just have one backing pump that is serving all of the primary pumps. So we could have a system where you don't have three backing pumps, but you only have one backing pump and that serves all of the systems. In our case, in the case of the Oxcart add-on probe here, it's a little bit more special. So we have really big non-evaporative getter pumps, so we don't have a backing pump, but the only backing that we do is through the buffer chamber. Yeah. So there's various ways of doing that, depending on what the specifics of the add-on probe are that you want to operate. I will just jump into the chemical leaps and show you what their pumping system is like, just simply because they are the most common add-on probes out there. For that, let me just create a new slide. And by the way, I will give you all the slides later as so you can print them out and take your own notes and do whatever you like. And so if you look at the LEAP vacuum system, what you have is you have the main chamber, then you have a valve that's going to the, oh, sorry, not into another valve, of course, but that's going into the buffer chamber. And then vertically on top of the buffer chamber, you have the load lock, which is a bit of an unusual configuration, but that's what it's like. And then you have a magnetically coupled transfer rod coming in from the bottom, and one coming in from the side. So the one from the bottom gets you from the buffer chamber to the load lock, and the one from the side here goes from. So this one gets you from load lock into the buffer chamber, and this one here gets you from the buffer chamber to the measurement chamber or main chamber. And as pumps here on the load lock, you have a turbo pump with 80 liter per second pumping speed, and this one is backed by a membrane pump. And it's actually the same on the buffer chamber. So you have a turbo with 80 liters per second, and again, you don't have to worry by now how turbos work. I'll explain it in detail later. And that is again backed by a separate membrane pump. And through that, because here we're open to air, you will typically get less than 10 to the minus 7 millibars, or you should get less than 10 to the minus 7 millibars. You should not actually transfer your samples in at a pressure that's worse than that. And here you should be less than 10 to the minus 8 millibars. So you should see a 10 to the minus 9 in the measurement. The main chamber is actually backed through the buffer chamber, just like in the case of our system. And here what you have is, as the pump, you have an ion getter pump. And this ion getter pump, I haven't looked closely, but it's a fairly big one. So I guess it's about 300 to 500 liters per second. I don't know, you can probably crawl in, if you have a LEAP add-on probe, you can probably crawl in and just look up which model it is and what the pumping speed of that one is. And that is the fundamental layout. And here, obviously, you've got a cryostat. And the cryostat here is a so-called Gifford-McMahon cryostat, or GM cryo. And that gets you down to around 20 Kelvin. Obviously, they have a little bit of wear on them, so the older the system gets, the less cooling power you will get out of it. but we will look in detail of what cooling power you get out of such a system. Okay, so this is the funny. Oh, and I just saw that I was drawing over the logo a little bit. So I hope you will still be able to see everything okay, especially if you get the handout. Sorry about that. I will pay a little bit more attention to that. Anyway, so by the end of the lecture, you should have understood how all the different components here work and how all the different components go together. If you want to make a very, very simple system, I think the simplest system you could think of to make an atom probe would be something along the lines of you have a measurement chamber, you have some kind of valve that goes onto a load lock. You pump this with a turbo pump with a backing pump and so then this goes out, and then have either a second turbo pump here, or pump it directly with the backing, and this would be fully sufficient to get to the pressures that you need to do atom probe tomography. Okay, but of course, usually if you buy a system, the system is made for throughput, so you don't want to spend a lot of money on a commercial system and then only be able to exchange 3 samples a day or something like that. Okay, and with that, let's jump back to the presentation. So you can see here, this would be typical implementations, and this would be sort of the simple implementation that I've drawn here, with 1 turbo pump here and 1 turbo pump here, and 1 common backing pump that you can use to pump down the entire system. Okay, and these would be typical atom probe systems, but you can also have atypical atom probe systems. And the reason why I'm mentioning that is because you might have some crazy experiments you want to do, or you might want to change the system that you currently have to do some special experiments. And I hope by the end of this lecture you should be able to at least competently think about how to do that. So on the left here, you could, for example, see an electron spectrometer in the physics department here in Erlangen that we can use and have used as an atom probe, where we can shoot special lasers onto the samples and things like that. And you can see this is François Bourpion, and something like that makes him very, very happy. And on the right side, for example, you can see our LEAP atom probe, where we have put some custom load lock on there so that we can do some cryotransfers. Yeah, so there's not just typical vacuum systems, there are also atypical vacuum systems. And hopefully by the end of this lecture, you're not as afraid anymore of them as you were before. So let's get to the sections of the lecture. So the sections of the lecture is, first of all, fundamentals of vacuum systems and vacuum vessels. So we'll go on to especially looking at ultra-high vacuum systems and what fundamentals we need to know here. How we do vacuum generation and vacuum measurement, how we do sample cooling, and how we do temperature measurement. So these are the 5 individual sections of the lecture. In the first section, in the fundamentals of vacuum systems and vacuum vessels, we will look at gas equilibrium pressures, operating ranges of pump types, and then how different materials fare in ultra-high vacuum. And we'll look a little bit in the design principle of ultra-high vacuum systems. So which flanges do we use and how to deal with them, and what sort of special design criteria we have in terms of gaps, venting holes, vented screws, and so on when we design an ultra-high vacuum system. Then we'll go into vacuum generation. The vacuum generation, we'll look into roughing pumps. I've mentioned some of the names already. So we'll look at these typical 4 versions of roughing pumps that are mostly used in ultra-high vacuum systems. This is not an exhaustive list, but these are the most common ones. And then the high vacuum pumps, the different high vacuum pumps that we can use to create an ultra-high vacuum once we've established a rough vacuum using the roughing pumps. And essentially they are pumps that remove the gases, the residual gases from the chamber, and they're pumps that are just trapping them. So they just absorb them or absorb them, so some kind of sorption or some kind of removal of gases. Then we'll go into vacuum measurement and look into rough vacuum measurement, so anything down to about 10 to the minus 4, 10 to the minus 5 millibar, and then high vacuum measurement, which means we have some kind of ionization gauges, and then combination gauges, which combine a rough and a high vacuum measurement, because they're also very, very frequently used in ultra-high vacuum systems. And you will find them on both commercial atom probes and non-commercial atom probes. Then we'll get into sample cooling and temperature measurement. And the sample cooling essentially will only cover approaches that are regularly used for atom probe tomography, which are closed cycle cryostats. And here we have GM cryoheads and Stirling cryoheads. And then liquid helium cooling, which is not as prevalent. But if you have access to liquid helium cooling, it's much, much more elegant than closed cycle cryostat. You will have noticed probably on various atom probes that you might have, some kind of vibration isolation, and that takes up a lot of design space on the atom probe. The reason for it is that closed cycle cryostats create vibrations, which, especially if you do laser atom probe, if you do voltage atom probe, it usually doesn't matter. If you do laser atom probe, it does matter. And their liquid helium cooling is the method of choice. But it costs a lot of money to put it in if you don't have it in your lab. But if you have it in your lab, always go with liquid helium cooling. And we will look at thermal conductivity, or generally thermal properties of materials at low temperatures, because they can be quite different than at room temperature. And then we'll look into temperature measurement. Essentially, how can we measure temperatures in the below 100 Kelvin range, which means we do resistance thermometry. With 4-wire bridges, we will look into how to do the resistance wiring and how to do the temperature control. And finally, we will then look into sample exchange and opening the system. So what kind of valves can we use in order to do sample exchange? Lids, valves. What are magnetically coupled transfer rods, or what other transfer rods do we have available? Which essentially would be edge-welded bellow operated ones, or something with corrugated steel bellows, because remember, we need to heat up the instrument, so we need to also account for thermal expansion to an extent. And then finally, we will look into working with ultra-high vacuum systems, which means we will be looking into how to clean UHV parts. So if you made something yourself, how do you clean it to be able to get it into your UHV system, or maybe you have contaminated some part that you already had. How do you clean it to be able to put it back into an ultra-high vacuum system? How to keep things clean, so which lab procedures need to be followed, and we'll look into bake-out procedures, which means how can I get any contaminant out of my system that is there because I opened it against air. And you can already see I've been talking for half an hour, so I don't know yet how long it's going to take, but I think it's going to be a longer lecture, but this should really give you all the fundamentals you need to operate any system that you have purchased, or understand how it works, and also potentially modify it or build a small system yourself. And I hope that all of you are as enthusiastic about all of that as I am, and will be able to stick through it until the end. Okay, with that, I'll finish the first section of the lecture. And the next section we're going to jump right in is going to be fundamentals of vacuum systems and vacuum vessels. So we'll start with sort of the basic physics of ultra-high vacuum systems, essentially. All right, with that, I'll see you in the next lecture.